Okay, this is section 2.2, and we're going to continue talking about sets, but we're going to focus this time on subsets and set operations. So first definition, we're going to talk about the universal set. The universal set is given by the symbol U and is the set of all elements being considered in a particular problem. All right, that's important because a lot of times when we talk about sets, we need to know what bigger population, what bigger universe that we're pulling these things from. If you talk about the set of registered voters, are you talking about the set of registered voters at Prairie State College? Or are you talking about the registered voters in Illinois? Are you talking about registered voters in the United States? The universal set, the bigger set that you're pulling from, is important. The complement of a set is written as A with this little symbol. It's a very easy thing to miss. All right, that symbol is so easy to miss. And also, complement mathematically is spelled different than compliment, as in to say something nice to somebody. That's spelled with an I. Mathematical complement is spelled with an E. All right, so it's written as A with that little symbol, or whatever the set is. If it's set B, then it'll have that little symbol. It's so easy to miss, though, so be careful. It represents the set of elements that are not in set A, but are still in the universe. Okay, so for instance, if my universe is the students at Prairie State, and set A is the set of people majoring in math, then what is a complement? So that's how we would read that. So a complement are the Prairie State students who are not majoring in math. So if A was people majoring in math, then a complement are people not majoring in math. Okay, set A is a subset of set B if every element in set A is also in set B. We write this with this little symbol that looks like a very smoothed out less than or equal to sign. And that's kind of what it means. It's A, and a lot of times we'll read this as contained in set B. Okay, so that's what it means to be a subset. It's part of another set. And it is kind of like a less than or equal to, because A is usually thought of as being smaller or equal to set B. A few things to note. Every set is a subset of itself by definition because of this or equal to option. And the empty set is a subset of every set. That's just kind of a default, right? Like, yes, of course, nothing is going to be smaller than everything. Okay, if A is a subset of B, but not equal to B, then we say A is a proper subset. Now look at the difference here. We really just take out that or equal to option right there in that symbol, and it's just called a proper subset. It means if it's not the or equal to option is just taken away from us. Okay, so let's look at some examples and let's label them as true or false. Now again, we got to read through some symbols and figure out what those symbols mean and what this problem is trying to say to us, and then is that problem correct? So my set of the two numbers 8 and 10 is a subset of the set of even natural numbers. So remember, natural numbers are 1, 2, 3, 4, 5, ... The even ones would be 2, 4, 6, 8, 10, 12, 14, 16, 18, forever. So yes, 8 and 10 is contained in this set. So we got 2, 4, 6, 8, ... So this is the descriptive way of writing the set. This is the list way of writing the same set. So this one, as far as, true or false goes, this one would be true. What if I reverse it? Okay, if I reverse it and I say, hey, is the set of even natural numbers, this 2, 4, 6, 8, 10, 12, 14, 16, is that a subset of 8, 10? No, this set is not completely contained inside this one. Remember, you can think of this as contained in or less than or equal to. That one is obviously so much bigger, so it can't possibly be smaller or equal to. So the direction that these are written is important, because one way it's true, the other way it's false, unless they're equal. If they're equal, then we flip the order and we get the same answer. Okay, the empty set is contained in here. Now you might be like, no, it's not in there. But remember, the empty set is by default a subset of everything. So this one's true. So just as a side note, the empty set is a subset of every set. I know I said the word set 3 times in there. Okay, how about the set ABC? Is it a subset of ACB? Well, yeah, they're equal. Remember how we talked in the last section about equal versus equivalent? And the order doesn't matter. So these two sets are equal, which is an option because of that little or equal to symbol right there. So this is true. So they just so happen to be equal. Okay, 4, 7. Is that set of just 2 things a subset of this one? Well, yeah, you can see 4 and 7 are both in there. So this set is contained inside this one. So that is true. All right, so now that we've decided what's a subset and what's not, let's talk about listing the subsets. The set AB, when we start listing all the subsets, I kind of do it systematically, okay? I always start with the empty set because I know I'm going to forget it. That's the set with 0 elements. And then I'll list out the set with 1 element, so just A, just B. And then I'll go up to 2 elements. Okay, well, this only has 2. So I've got 1, 2, 3, 4 subsets. So that's where this answer comes from. If this increases to 3 elements in a set, now look at how many subsets I got. I've got the 0 element subset of the empty set, and then the 1 at a time elements. Okay, that's just A, just B, just C. And then I take them 2 at a time, A, B, A, C, B, C. Then I take it 3 at a time. Here I've got 1, 2, 3, 4, 5, 6, 7, 8 total subsets. Now you can see how this can get out of hand really quickly. If I start having like 4, 5, 6 elements, I'm going to have a lot of subsets. So there's actually a shortcut. The number of subsets is always 2 to the n power, where n is the number of elements in the set. N is the cardinality. So here, 2 elements. That 4 right there came from 2 to the 2nd power. This is 8. Look, 1, 2, 3 elements. So it's 2 to the 3rd power. Now, be careful, that's not 6. That's not 2 times 3. 2 to the 3rd power is 2 times 2 times 2. So 2 times 2 is 4. 4 times 2 is 8. So the 2 is set in here. The number up here, the exponent, is the cardinality, or the number of elements in that set. So it's actually a pretty handy little shortcut, which is going to come in handy here. So example 3, find the number of subsets. Do not list them out. Trust me, you do not want to list those suckers out. Okay, so we're just going to use the, grab my calculator here. Let's use that little shortcut that I showed you. So here we've got 1, 2, 3, 4, 5, 6, 7. Okay, so there's 7 elements. So the number of subsets is 2 to the 7th power. So let's bust out a calculator for that, okay? The exponent key is right here. It's that little up arrow looking thing. So if we hit 2 and that little up arrow and then 7. Now some newer versions of the 84 Plus will actually display that 7 kind of up a little bit, kind of how it's written. So mine's a little bit older, so I don't get that little perk. But 2 to the 7th power is 128. So there's 128 subsets. Yeah, let's not list those out, right? Definitely not. Okay, this one though says find the number of proper subsets. That just means that I have to subtract 1 because proper subset just takes out the or equal to option, just takes out that one option. So the number of proper subsets is that 2 to the n minus 1. So here I've got 1, 2, 3, 4, 5, 6, 7, same as up here. So the number of proper subsets is going to be this 2 to the 7th and then minus 1. Be careful, it's not 2 to the 6th. The minus 1 is not on the 7. So it's that 128 that we just got up here, but minus 1. So it'll be 127. Okay. We can represent sets visually using what's called a Venn diagram. This Venn diagram is a rectangle, and everything inside the rectangle is the universe. Then for each individual set inside the universe, we tend to use circles. So this would be set A, which is contained in the universe. We're going to do more with Venn diagrams in the next 2 sections, but for now we're just going to kind of do a little slight introduction. Okay, so the Venn diagram for A. If I just draw like a single circle representing A, and I just want to represent, hey, where is set A? I could shade just inside that circle. If you see it with 2 circles, that's how we often see Venn diagrams. If you see it with 2 circles, A and B, then set A, again, is just everything inside circle A. Okay, so set A here is just everything inside circle A. Same thing over here. It's everything inside circle A. Yes, some of it overlaps into B, but that's okay. A complement, remember that complement meant not. So this means the stuff not in set A. So you'll notice I shaded everything that was not inside A. Same thing over here. I just happen to have 2 circles, but look, everything inside the circle is A. So I shaded everything that was not inside circle A. And then the A is a proper subset of B. That means A is completely contained inside B. Now, it could be that A is a little bit bigger or whatever, but A is contained inside B. That's how you would draw that. All right, so with Venn diagrams, we talk about the intersection and the union. So if you have any memories, any fond memories of Venn diagrams, they probably involve this stuff, okay? We've got this intersection or the overlap of 2 sets, okay? The set of elements that are in both sets A and B are right here. It's the overlap of the 2 sets. We use this symbol right here to represent intersection. Not to be confused with the union. The union are the elements that are in A or B or both. For that one, we use this U. Now, you might think, oh, that's a lot like the universe, and it is. The universe, we tend to have like a little leg on it. But yeah, U right here for union. Okay. Intersection is just both, overlap. The union is the both, but with more. It's the one or the other or both. So I want you to think of union like a blended family. right? So we've got, person A over here, and maybe they had like a kid, and then person B over here, maybe they had a couple of kids, and then they get together and maybe they have a kid together. And now you've got that whole family all blended together. So that's your union. It's that beautiful union of that blended family. The intersection, as far as the family goes, would just be the kids that they had together, right? So you can kind of think of that as being the difference between those. Okay, so let's look at a specific example here. So we're going to use the Venn diagram to find the elements in the sets below. A union B. So remember, union is one or the other or both. So I want you to see union, and I want you to immediately think anything in either circle or both. Okay, so either circle or both. So we got 3, 1, 7, 4, 8, 2. The order does not matter. It's okay if you write the same thing, but in a different order. It's okay. Now just note that when you put this answer in ALEKS, if you forget those little curly braces, it will mark it wrong. It's petty like that. All right, so just know that going in. I can change your grade and make it correct if you point it out to me. Okay, intersection. So visually, the intersection is just the both. And I realize I just drew those a little bit too small, but so it's just the overlap. So it's just right there. So it's just the 4 and the 8. So I'm just trying to kind of take you back to the previous page and visualize where the union is, where the intersection is. This is the complement. So it's the stuff not in circle A. Okay, so remember, not. Boop. All right. So this is circle A right here. So we're looking at circle A. What are all the things that are not in that circle? So I'm just covering up that circle. What are the things not in that circle? What, 6, 5, 2? Don't count you. That's just your label. That is not something in the set. This is just a label, just like B is a label and A is a label. Okay. So the stuff not in set A would be the 6, the 5, and the 2. The U is your universe, not the union. So don't get those mixed up. The universe is everything inside the entire box, okay? A lot of people will mistakenly think it's just 6 and 5. It's just this outer part, and that's not the case. The universe is everything. So it's 6, it's 5, it's 3, 1, 7, 4, 8, and 2. So it's everything in that rectangle. Okay. So this one, I asked you for the union, the intersection with it given in this kind of visual form. Here, we have it in list form. So these might be a little bit harder, okay? So A intersect B. This is the overlap. Okay, so the overlap. What are you barking about? Okay, my yappy little wiener dog goes barking at everything. All right, so this means the overlap. So it's what they have in common. Okay, so we have A and B. So let's look at A and B. What elements are in both A and B? Is 1 in both sets? No. 3, 5. There's nothing that they have in common. Okay, so we can write that as either the empty set or that symbol. And Alex will give you the option of either one of those. But it just means there's nothing that those two sets have in common. All right, how about A and C? What do those have in common? Where is their overlap? Well, let's look at A and C. Oh, they have 1 in common. Ooh, and they have 3 in common. Okay, so shared, they have 1 and 3. Remember that you do need to put the set symbol there, or Alex will mark it wrong, because you do want to say, okay, hey, this is a set of elements 1 and 3. All right, this is the union. So the intersection is just the overlap. The union is the stuff in A or C or both. So the way I want you to do this one is we're just going to write everything in A and then smush it up against everything in C, but just don't write anything twice. So let's smush A and C together, but don't write repeats. Okay, so that would mean A is 1, 3, 5. C is 1, 2, 3, 4. But I'm not going to rewrite the 1, 2. Okay, 3 I already have. I'm not going to write it again. And 4. So for the union, we're just going to smush the sets together. Don't write any repeats. The overlap are those repeats. Okay. So I'll have to do some flipping back here. This is the stuff in the universe, but that's not in set C. Okay, so we got to go back, see what the universe is. The universe is the numbers 1 through 10, and C is 1, 2, 3, 4. So that means that C complement is the rest of this set that's not this. So instead of 1, 2, 3, 4, it's going to be 5, 6, 7, 8, 9, 10. So 5, 6, 7, 8, 9, 10. Now, you might say, well, how did you know to stop at 10? How did I know not to keep on going? That's where the universe comes in. The universe tells me, hey, I'm just looking at the numbers 1 through 10. C is 1, 2, 3, 4. So not C is not 1, 2, 3, 4. It's everything else in the universe. Okay, this one is the set B intersected with the universe. So remember, intersection is the overlap. It's what those two sets share, what they have in common. So if I look at B, 2, 4, 6, 8, and the universe, 1 through 10, what do those have in common? Well, 2 is in both sets. 4 is in both sets because that's what these ellipses mean, that the pattern keeps on going. 4, 5, 6, 7, 8, 9, 10. 6 is also in there. 8's also in there. So we get the entire set of B, which is 2, 4, 6, 8. Now it turns out that if you take the union or the intersection with the universe, you're always just going to get that original set back. Okay, so 2 more, and then we'll finish up this section. The universe complement. Okay, so if complement means the stuff in the universe that's not in this set, what's the stuff in the universe that's not in the universe? Well, there's nothing in there. So you can kind of look at it as, hey, what is the opposite of this everything here, right? What's not everything? So if I take away, if that's what complement does, is remove the universe, then you have nothing left. So it's the empty set. Similarly, this is the empty set. If I look at the complement, it's everything in the universe that's not in the empty set. Well, that means take the universe 1 through 10 and remove nothing, right? That's what that means, remove nothing. So that just gives you back the universe. So you can write it as U for the universe, or if you want to write it in list form, then either one of them would be okay. Pretty sure that in the homework that Alex will actually have like a little symbol for universe that you could use, but you could also just write out, whatever that set is in list form and it'd still be okay. Okay, so that finishes up section 2.2.